Hello chemistry girls, I'm making you a new video this time to talk a little bit about something called a reaction mechanism. This is to help you with the reading that you do in the chapter in section 11.7. Also some Brightstorm videos that I'll link for you. As you can see by my notes here, a reaction mechanism is a sequence of steps by which a reaction occurs at the molecular level. And one thing to keep in mind about everything we do here is that you're not supposed to be able to figure out what the mechanisms are. This is done by someone who studies reactions very, very carefully on a molecular level. So we just need to know how to answer a few questions about mechanisms that are presented to us. So keep that in mind. You're not supposed to be able to figure out the mechanism. You just need to understand a little bit about what you're seeing. So in my example here, I've got the overall reaction between carbon monoxide and nitrogen dioxide, forming the products of nitrogen monoxide and carbon dioxide. And when this reaction is studied, it turns out that it doesn't happen just exactly like the reaction suggests. In fact, there's a two-step process that you can see written in blue down below. The first step is actually when two NO2 molecules run into each other and they form the products that you can see there, NO3 and NO. And then the second step of the process occurs when a carbon monoxide molecule runs into one of these NO3 molecules to form the products. And I've outlined the NO3 in red like that. That's a kind of a common thing when you're looking at a mechanism, and that's what's known as a reaction intermediate. It's kind of a temporary thing that only exists for a few moments during the reaction, or if you can see my notes here, you can also say it's a substance that's produced in one step and then consumed in a later step. One thing to notice is that if we combine the two steps, kind of like almost like a Hess's law type of combination, if we combine the two reactions, they add up to the overall reaction that we started with, and the NO3 is kind of a canceling out item. In a mechanism, that's what's referred to as a reaction intermediate. And then the term elementary steps is used. I've just labeled these as steps of the mechanism, but they're officially referred to as elementary steps. Now, the thing about the mechanism is that, again, people who study this very carefully can figure out what the different steps are, and they can also study the rate of each individual step. How fast does step 1 occur? How fast does step 2 occur? They can study all these things. And it turns out that each individual step has a rate law, very much like we write rate laws. We've been learning to do that for other reactions. The big difference is that if you want to write a rate law for one of these elementary steps, you can automatically write it down according to what you see. In other words, coefficients are used as part of the rate law. That's exactly what you can't do when you're trying to figure out the rate of some overall reaction. But if you're looking at just a single step, single elementary step, in a mechanism, then it is true that you can just automatically write down a rate law for that step. So for example, if this is my step 1 from above, and I wanted a rate law just for this step, it would look something like this. Because I can see two NO molecules hitting each other, then the rate of this reaction would be written as K1 times NO times NO. Or in other words, NO squared. The 2 would be a coefficient. If I'd chosen to write this just as 2NO2, then the 2 would be a coefficient. And I've labeled this with a little K1 just to remind us that it's coming from step 1. This isn't necessarily the rate for the whole reaction, it's just a rate for this step. Same thing for the second step. How fast does this step occur? Well, the rate of this second step would be equal to its rate constant times CO to the first power and NO3 to the first power. We can automatically say that because both of those substances have a coefficient of 1, and that allows me to automatically write down a rate law. You can do this little simple rate law writing when you are dealing with the steps of a mechanism. So if you tried a few examples, these are just some answers. If you looked in your book on page 318, you could see the original questions. but basically the directions say write the rate laws for each of these mechanism steps. And they don't show you the entire mechanism, but they do say that these are all mechanism steps. So if you wanted to take a look at those questions and pause the tape while you did, then you could take a look at the answers that I came up with here. And each of these would be very quickly written down simply according to what you see in the problem. The next thing we have to talk about if we're learning about mechanisms is the idea of a rate determining step. And the definition of this is the slowest step that's identified in the mechanism. The same people who study and figure these mechanisms out in the first place also identify which steps will take place more slowly and which steps will take place more quickly. And that's just very common. If a process is happening step by step, sometimes one of the steps can be very quick. Meanwhile, you have to wait for something else to happen. So for example, this original mechanism that I showed you, let's say that someone not only showed us the mechanism but told us here off to the side that this step 1 is a slow step, meanwhile the step 2 is a fast step. And that's important because of what it says down here in red. What we know about the mechanism is that when you've identified the slow step of the mechanism, the rate law just for that step should be the same as the overall rate law. They have to match up. And there are lots of questions that are based on the idea of the rate law of one slow step matching the overall rate law. So back up here to my example, the first step is identified as the slow step, and its rate, the rate of just that step, would be k NO2 squared, because as if there's a coefficient of 2 here. Now, does this equal the overall rate? It would have to, maybe someone would have figured out by doing one of those other experiments to figure out what the overall rate is for this reaction. And if that overall rate ends up being the same as just this step's rate, then our conclusion is that the mechanism is considered consistent with the overall rate. You'll hear that wording again, the idea of a mechanism being consistent. But the statement in red there is the important one. When you have a mechanism that's broken down into steps, and one of the steps is identified as the slow step, it needs to work out so that the rate law of the slow step in the mechanism matches the overall rate law. So here's an example. Let's say I have an overall reaction here with hydrogen reacting with this compound ICl. Anyway, we've got an overall reaction here. Someone has worked out for us that the overall rate law for this reaction is K H2 to the first, ICl to the first. In other words, they figured out by calculation and experiment that this reaction is first order in hydrogen, first order in iodine chloride. So this is our rate law. Someone else has studied this and just proposed this mechanism for the reaction to take place. They are having us imagine that we start with this particular step, identified as a slow step, and then it would be followed by a step 2 here. Notice, although I didn't circle it, notice that this mechanism includes an intermediate substance. This HI substance would be produced here and consumed here. It would cancel out if we went to add up these equations, and so that means that it's identified as an intermediate. Anyway, what we're trying to do is to show that this mechanism is consistent. Does this blue mechanism match up in some way with this overall rate law? And you really have to do two things. To prove that a mechanism is consistent, you have to show that it adds up correctly. Do these two steps add up to give us the overall rate law? Almost always that's the case, but officially we should really check that. The more important thing we're going to talk about right now, though, is the rates of the steps. If this mechanism is going to be considered consistent, then we would have to show that the rate of this slow step matches what we've been told is the overall rate. And this is a pretty easy one to do because the slow step is step 1. And it would have a rate law written automatically as K1 times concentration of H2 to the first power, concentration of ICl to the first power. That's the rate of the step. It's also the overall rate for the reaction, and what that means is we say, yes, this is a consistent mechanism for this reaction.